Hi, my name is Lucas Brasher. I am a BS in Computing Engineering from a Brazilian university named State University of Campinas, and currently I'm studying Baroque cello at Guido Cantelli Conservatory in Novara, Italy. And I'm glad to share with you something that I've learned in my personal research. Before we go on, I would like to apologize for any grammatical, syntactical, or pronunciation errors since my English became my third language, and I don't have practiced it so much, so it became a little bit rusty. So I apologize. So I would like to talk about timbre, old school synthesizers, and a little bit of mathematics. In the sense, we'll use ideas behind internal workings of a classical synthesizer in order to show a first approximation on how timbres are mathematically modeled. But let's begin with the ending part. Let's explain quickly how a loudspeaker works. Um, there are a lot of different models of loudspeakers in the market, but in a nutshell, a loudspeaker can be modeled as a membrane attached to a magnet that runs freely inside a coil. And if you apply electrical current on this coil, the magnetic field generated inside this coil will attract or repel the magnet in it, and thus make the loudspeaker membrane go back and forth. Basically, this is the way a common loudspeaker works. And uh, and uh, that's what electrical signal does to the loudspeaker. And every single frame in a sound sample is indeed a kind of geographical coordinate of the loudspeaker membrane. For instance, in a normal audio CD, every frame of sound sample has 16 bits, and we have 44,000 frames per second. And what does it mean? It means that a CD sends coordinates to the loudspeaker membrane 44,000 times per second, and each coordinate has 16 bits, meaning 2 to the 60, it's equals more than 65,000 different positions for the membrane. It's a high granularity, meaning the membrane can be put to a very forward position and a very back position, and more than 65,005 different positions between these positions, and and a rate of 44,100 times per second. But it's a little simplification, because we can also have harmonics on membrane and other phenomena like Clarinet patterns, but this will be not covered here. And if you are very fast and accurate about changing quickly the amount of energy on a coil, and put every time an exact quantity of energy in the coil, you will be put will push and pull the loudspeaker membrane back and forth as you want, and thus you will compress and decompress the sound in front of it as you want, and so you generate any sound you want. But to do this manually, it's practically impossible, so we use some function generators in order to do this. And the most common generator is the Sine generator, and we will analyze the generator on the next minutes. Okay. Basically, a sine generator generates an alternate current in a sine wave fashion. For instance, the wall socket generates a sinusoidal alternate current, and that's why you hear a constant hum at 60 or 50 hertz when using a washing machine, for instance. Depending the frequency of the power outlet you leave, you hear 50 or 60 hertz. To our ears, the 60 hertz correspond roughly to a B flat, and 50 hertz corresponds roughly to a G note. And obviously, if we connect our loudspeaker to the wall socket, it will probably explode. So don't do this, okay? In fact, you need a sine generator that matched in voltage and current the loudspeaker specifications. The sinusoidal generators inside of a synthesizer does this perfectly. And when you connect a sine generator to a loudspeaker, you will hear a pure sine wave with the same frequency of the generator, and it sounds like this, for instance. Only a minute. Okay, this is the way a pure wave sounds in a loudspeaker. And uh, this idea of using only a minute, I've lost. Okay, and this idea of using a pure sine generator to play sound is the core idea behind a sound synthesizer. But a synthesizer normally doesn't use a pure sine to make a sound, but it uses a method to synthesize the sound. And one of these methods is the harmonic additive synthesis that, put on simple, amplificates or attenuates some of every audible harmonics of the bass frequency, and then, so to say, make a sort of sum up of these harmonics in order to generate the synthesized timbre. Indeed, it's not a sum, it's more like an arithmetical mean. And when these harmonics are summed up and put on the coil of the loudspeaker in form of electrical current, it will generate constructive and destructive interferences, and then will make the loudspeaker membrane go back and forth in different ways with the same bass frequency but with different harmonics, and so with a different timbre. Okay. And so using the harmonic additive synthesis like an old Moog synthesizer does, we can set the amplification of some harmonics in order to try to reproduce the sound of existing instruments. In fact, there are some recipes of how to put the correct gain on each harmonics in order to make timbres and mimetize an instrument. And this is a very neat thing, and here we present the partial harmonics for two instruments. We have the clarinet and oboe here, and this table says that the first harmonic, so the bass note at the clarinet, must be neat to amplification to 100%. The second one, 5%, the third, 20%, and on and on. It's only a simplification also, because in a harmonic additive synthesis we have also the phase shift, but we will not cover it here also. Okay, let's go on. But you can ask me, this works? And well, since I have that mathematical itch, and since I'm a computer engineer, I decided to write down a piece of code that uses the soundboard in a very similar way to an old synthesizer like Moog. I know that it's very weird, but I wrote down in C this one pipe model that can sound an harmonic series and sound a set of harmonics with determined gain to each harmonic. And let's see this working. Let me put it here on the screen. Okay, so just to show you quickly, I know it's C, it's very complicated, but I did here a function to play a series of harmonics. It opens. I got some code from shiftfont.org, and I know it's a very messy. I wrote here this code in a hurry, but it works. It plays. It gets a set of frequencies and play each frequency at a time at the soundboard. And here we have the play of partials that get a set of frequencies and the set of amplifications of each frequency and play it all together. We can see here that I construct the samples here, getting the sine, the value of the frequency, and the amplification factor for each frequency. So let's see this working here. Let's load Python and make the import. Okay, so let's play a little series of notes here. Let's put an initial frequency. Okay, and let's hear it how this sounds. Okay, you know, it was a little bit strange because we have some very high pitch here. It sometimes it's not so nice to hear, but all the sounds in the nature have this series of harmonics. So, but I now I put all of these in a very amplified way. But we can also change and play other series based on other frequencies. But when we hear these sounds, this is what happens. When I store when in the variable a frequency of, for instance, 44 hertz, I ask the computer to play the frequency A, means 44 hertz, and 2 times A, 880 hertz, and 3A, and 4A, and on and on. And I send it to the loudspeaker that moves the membrane accordingly, compressing and decompressing the air, generating the sounds. Okay, but what's the matter about that? The matter is, if you know the amount of amplification or attenuation to every harmonic, you can simulate with some accuracy a timbre of an existing instrument. So let's try to construct piece by piece the synthesized sound of a clarinet and oboe using that table that I showed before and the harmonic additive synthesis. And googling up these things, I found that little recipe that you saw here on how construct these sounds. And this is a table of amplification attenuation for the first 9 partial harmonics for synthesizing the clarinet and oboe. Okay, let's see this working. I'm putting now the first harmonic of 100% of gain. It means that the loudspeaker membrane will vibrate to the frequency of that frequency with a 100% of amplification. And I mean the 0 dB full scale. But before this, let me change to a little bit comfortable frequency and play it to you in a minute. Okay, you heard an E note, that is a note for the 330 hertz. And now let's sum to the this note a second wave of 660 hertz, but only with 5% of amplification. So let's hear it in this video. Okay, the sound became a little bit different, and we can successfully put the other partials with the respective amplifications. I don't do that to every partial, but I put the final result to you hear how an synthesized oboe sounds. Okay, I know that it was not a perfect oboe sound, but it's almost there. Now I get that table that showed you with the clarinet partial amplification to the all harmonics and play it here, and we see that it's very different and it sounds almost like a clarinet. Okay, so we have reproduced here two different sounds with two different timbres modulating the amplitude of the respective partials. Um, so I hope you have enjoyed this little video, and thank you all for watching. And I would like to say this video was probably made with free software, and I used GCC, Python, LibreOffice, and Record My Desktop. And thank you all for watching.